उत्कर्ष केंद्र वाले हैं पॉजिटिव लक्षणों का मध्य पॉजिटिव लक्षणों का कमर कितने हला है
ध्यान वाले प्रकाश मानते जिन जिनिष्टा उठी
सेटा हला पंच है हां और पंच है से रेशियो है
ये रेसिपी होती 2.5 समझ लगे बोलो ना पवित्र आती नहीं वाले
very good afternoon to all of you. I myself IQAC coordinator. Welcome to the webinar organized by Department of Mathematics, Pattamundai College, established way back in from last 51 years. It has completed 51 years of its journey in the education arena of state. And we coordination with the IQAC are organizing a blended mode of process, and part of that process we are organizing a series of Department of Mathematics is one of the leading departments in which the alumni are well established in India and also around different corners of the world. The department is headed by Professor Aravinda Pandab and another man who is present in the department, Dr. Nirmal Kumar Sahu. Nirmal Kumar Sahu. They are doing well in the department by organizing various intellectual deliberations. It is my proud privilege to welcome our today's speaker, Professor Prasanta Kumar Roy, Professor from School of Mathematics, Sambalpur University, Sambalpur. And the second speaker is Dr. Bijoy Krishna Debnath, Assistant Professor, Mathematics, Tezpur University, Assam. And the today's topic is balancing numbers and their related frequencies, balancing numbers and their related and overview. The second topic is it talks on inventory modeling. Inventory modeling. Once again, I want all the participants also from the outside state this webinar, and now I request Head of the Department of Mathematics, Professor Aravinda Pandab, to give formal welcome address. Mr. Pandab.
Very good noon to all of you. Honorable Chairperson of the Organizing Committee and Principal of the College, Professor Prabhakar Rao, respected Resource Person Professor Prashant Kumar Roy, and Dr. Bijoy Krishna Debnath, renowned readers, lecturers, research scholars, alumni of this college, and my dear students. Really, it is a proud moment for the Department of Mathematics, Pattamundai College, Pattamundai, that we are organizing a national level webinar on balancing numbers and their related sequences, and a talk on some inventory modeling, in which we are fortunate to have listened mathematicians as resource persons. Let me clarify, this webinar comprises two technical sessions. In first technical session, topic is balancing numbers and their related sequences, where Professor Prasanta Kumar Rai is the resource person. In second technical session, the topic is a talk on some inventory modeling, and the resource person is Dr. Bijoy Krishna Debnath. So let me introduce our resource persons to the participants. Professor Prasanta Kumar Rai is now working as Professor of Mathematics, School of Mathematical Science, Sambalpur University, Burla. He started his career as a lecturer from Dalmia College, then College of Arts, Science and Technology, Pattamundai, Rourkela. Then he was Assistant Professor of Mathematics in C.V. Raman Engineering College and also in IIIT Bhubaneswar. He was also Associate Professor of Mathematics in Veera Surendra Sai University of Technology, Burla, from 2015 to 2017. And from 2017, he is Professor and continuing as such in Sambalpur University. Regarding his education, he completed post-graduation from Utkal University, Banibihar, and got PhD from NIT, Rourkela. So far as membership of professional bodies is concerned, Professor Rai is the life member of Odisha Mathematical Society and Indian Mathematical Society. He has attended and presented paper in conferences of international reputed university like Augusta University, Georgia, USA, La Trobe University, Bendigo, Australia, Wuhan University, China, and a conference that is ICC 8 in 2014 in Thailand, and University of Bordeaux, France. So we are fortunate to get such type of legend mathematician as resource person. So far as national level conference and workshop is concerned, Professor Rai has attended 8 conferences in which he has presented 6 papers. Regarding his publications, he has published from 2005 to 2020, more than 30 publications are there. Sir, department is happy to get you as resource person for this webinar. I welcome you, sir. Now, our other research portion, second research portion, that is young and energetic mathematician from North India, northeastern of India, Dr. Bijoy Krishna Debnath. Dr. Bijoy Krishna Debnath is currently working as an Assistant Professor of Mathematics at Department of Applied Sciences, School of Engineering, Tezpur University, Assam. Dr. Debnath is well known to Odisha because prior to that he was working as an Assistant Professor at Government College of Engineering, Kolahandi, Odisha. He did his PhD in Operation Research from National Institute of Technology, Agartala, and Master degree from Guwahati University. His areas of research includes operation research, fuzzy mathematics, and optimization. Mathematical modeling. He has published research articles in so many reputed journals of and international report that includes International Journal of Operation Research and Active Journal of Mathematics and Statistics, International Journal of Logistics System and Management, Iranian Journal of Fuzzy System. Sir, I welcome you this noble occasion to this webinar. Thank you. It's over to Dr. Sunil Kumar Pradhan, sir, IQAC coordinator of this college.
Thank you, Mr. Arvind Pandav. Now, I request our first resource person, Professor Prasanta Kumar Ray, from School of Mathematics, Sambalpur University. Professor Ray, are you listening to me?
Yes, sir. Yes, sir. I'm audible to you. Okay. Yes. Can you hear me? Hello. Can you hear me? Okay. Okay.
So let us start.
Now I can. Okay, sure. So I think I can share my. So you can do, Mr. Pandav, Dr. Pandav.
Yes, sir.
So you can do as a co-host, I think. Co-host for me, so that I can share my screen.
Professor Ray.
Yes, thank you. Yeah, I'm sharing my screen, sir. Okay.
Yes, sir. Yes, sir. Yes.
My screen is visible to everyone?
Yes,
Hello?
sir. It's visible.
Okay. My screen is visible? Yes. Okay.
Yes.
So I request you all to please mute yourself. Okay. All the participants are requested to mute. Okay. So that I can speak. Okay. So my topic is balancing numbers and their related sequence and overview. Though that was my topic, but I would tell a little about the mathematics, and I have collected, these are all from the internet. Okay, so you might have seen all these things in social media. Am I audible? Am I audible?
Yes, sir. You are audible, sir. You are audible, sir.
Okay. So I have collected from the internet, and you might have seen all these things from in social media. So these are some codes of mathematics. Before I will start my main topic. First of all, I would like to thank the organizer for inviting me and giving me opportunity to deliver this talk in your seminar. So I am thankful especially to Dr. Pandav and his team, and especially principal of this Pattamundai College and other member of the Pattamundai College. So my topic, before I will start, I would like to tell about some codes that are some serious codes and some funny codes. These are for the students, and most of the participants may be the students perhaps. So mathematics is not about numbers, equations, computations, or algorithms. It is about understanding. And without mathematics, there is nothing you can do. Everything around you is mathematics. Everything around you is number. This quote is by Shakuntala Devi, famous mathematician, you know. And it is also, I think you will agree, all of you agree with me, that 4 out of 3 people struggle with mathematics. This is one quote. Mathematics may not teach us how to add love or subtract hex, but it gives us hope that every problem has a solution. And this is the famous quote by George Polaya. Mathematics is the cheapest science. Unlike physics or chemistry, it does not require any expensive equipment. All one needs for mathematics is a pen and paper. Life is a math equation. In order to gain the most, you have to know how to convert the negative into positive. So this is more funny. So it is an equation. Life plus love is always happy, you know. And life minus love, that is without love, it is always sad. So if you add these two equations, this gives 2 life, which is equal to happy plus sad. And life is happy plus sad by 2. That means it is true that life is half happy and half sad. This is the mathematics of life. And you know that from Vedanga Jyotisha explained the importance of mathematics among sciences. Yatha sikha mayuranam naganam maneyo yatha tadvad Vedangra sastranam ganitam murdhani stitam. Like the crest of the peacock, the meaning of this sloka is like this. Like the crest of the peacock, like the gem on the head of the snake, so is mathematics at the head of all knowledge. And in Bhagavata, you see, we have a sloka, this one, in Upanishad. Punnamadha punnamidam punnata punnamudechyate punyasya punnamadaya punnameda vashishyate. Om Shanti Shanti Shanti. So this one actually comes from, you see, these are the letters Kadinava, Tadinava, Padipanchaka, Yadastaka, and Khyasunyam. Kadinava means 9 letters. Ka, Ta, Pa, Ya, up to 9. They are treated as one. Tadinava is 9 letters again. It starts from Kha, Tha, Pa, and this is again 9 letters. And these are Padipanchaka, these are the 5 letters. Gna, Na, Ma, and Sa all represent 5. Yadastaka, 8 letters we have. It starts from Ja, Da, Ha. These are all symbolized letters. Okay, Ja stands for 8, Da stands for 8, and so on. And Khya Sunya means Khya stands for 0. So using this, there is a sloka on God Krishna. So this gives the value of pi. You see, 3.14 up to 32 decimal places. This is the sloka, Gopi Bhagya, Madhuvrata. Okay, so this gives here, if we take Go, Pi, Bhagya, so if we arrange the letter in terms of numbers, and you will find that this gives the value of pi that is in 32 decimal places. Okay. So there are some funny theory also, so I don't want to tell because I will go directly to my topic. Okay. So am I audible? Am I audible? Am I audible?
Sir, you are audible, sir. Audible, sir.
Okay, okay. Okay, okay. Thank you. Thank you. So I will start with this interesting number. This is called the triangular number. So triangular number, why I will tell? Because it is related to the balancing number, the main topic that I want to say today about the balancing numbers. As you know, I am a man of number theory. My research interest is number theory. And the famous mathematician Gauss rightly said that mathematics is the queen of all sciences and number theory is the queen of mathematics. Okay, so this subject, number theory, is a very interesting subject among ancient times. Many researchers, they have done many things on number sequences, number theory, numbers and number sequences. So from the ancient Babylonian time, they connect, the people connect numbers with figures. They are called the figure-eight numbers. Okay. So figure-8 numbers are actually triangular number, square number, pentagonal number, and etc. So I will concern on the triangular number only because it is related to the balancing number. Carefully listen, please, the definition. So the first dot represents the 1-point triangle here. So first triangular number I can say T1. Let us, if we write it as a T1, T1 is 1 because 1 point represents a triangle. This next one is 3 points represent a triangle. So next triangular number T2 is 3. So you see the third one. Third one is 3 plus 2 plus 1 gives us 6 numbers. So T3 is 6. T4, 4 plus 3 plus 2 plus 1. That is 1 plus 2 plus 3 plus 4. So T4 gives us 10. So one can easily say, what about T6? T6 is 1 plus 2 plus 3 up to 5. Up to how much? 6. Up to 6. So 6 into 7 divided by 2. There is a formula, you know, that if it is 1 plus 2 plus 3, that is the sum of the first n natural number is n into n plus 1 by 2. So one can easily say that the nth triangular number, that is Tn, is in n into n plus 1 divided by 2. So from that we can find T100 also. T100 is 100 into 101 divided by 2. That means 50 into 101. Whatever value gives us the 100th triangular number. So this is the way to find out the triangular number. But there is another definition of triangular number also. Any natural number n is called a triangular number if 8n plus 1 is a perfect square. It is a perfect square. It means square of a positive integer. So for example, what I have already told you that 1 is a triangular number. You can verify. 8 into 1 plus 1 gives us 9, which is a triangular, which is a perfect square. Next triangular number is 3. We can put here 8 3 is 24 plus 1 is 25, which is a perfect square. Next one is 10. 8 10 is 80 plus 1 is 81, which is 9 square. It is a perfect square. So the definition is any natural number n is said to be a triangular number if 8n plus 1 is a perfect square. Okay, right. So this is the definition of triangular number. So please remember this one because this is useful while defining the balancing numbers here. The main topic that I want to say today. Okay. Next. Yes. Okay. I have already shown this one in your previous talk, but maybe the audience are new. Again, I am repeating this one. It may be fun to you. There is a number called happy and sad numbers. I want to share this number again because I have already told you, friends. This the definition says like this. A happy number is defined by the following process. Starting with any positive integer, replace the number by the sum of the square of its digits. For example, suppose the number is 10, whether we will verify whether 10 is a happy number or not. So replace that number 10 as 1 square plus 0 square. That means sum of the square of its digits. If I will get 1, you see the value is 1 here. So directly we are getting 1. So it is a happy number. Another example is 23, say. 23 can be written as 2 square plus 3 square. 2 square is 4 plus 3 square is 9 gives us 13. 13 can be written again as 1 square plus 3 square gives us 10. And 10 can be written as 1 square plus 0 square gives us 1. That means ultimately while when we are adding the square of its digit, if you are getting 1, then it is a happy number. And if you are not getting 1 and the process is not end, it forms a cycle, then in that case we call it is an unhappy number or sad number. For example, I am taking some example, you see. Suppose 4, you see, number 4. This number 4 is a happy number or unhappy number. Let us verify. See the arrow mark. 4 is represented as 4 square. 4 square is 16. Then that process is repeated. 16 means 1 square plus 6 square gives us 37. 37 arrow mark again. 3 square plus 7 square is 58. 5 square plus 8 square is 89. 8 square plus 9 square is 145. 1 square plus 4 square plus 5 square is 42. 4 square plus 2 square is 20. Then 20, 2 square plus 0 square is 4 again. What does it mean? This never ends. 4, if that 4 will come, then we again that process repeats. That is 4 gives 16 and so on. It forms a cycle there. It means that we are not getting 1, so 4 is an unhappy number. Okay. So this is the definition about happy and unhappy numbers, right? Okay. So there is a picture of happy number. These are some happy numbers between 1 to 30. You can verify. 9 to 1 is a happy number because it goes to 1. 1 is in red color, marked by red color. 70, see the arrow mark. 70 means 7 square plus 0 square. Then 49, 4 square plus 9 square. 97, 9 square plus 7 square, 130. Then 1 square plus 3 square plus 0 square is 10. 1 square plus 0 square is 1. So ultimately all the numbers goes to 1. Therefore these numbers are happy numbers. But see the picture of, this is a beautiful picture of unhappy numbers. You see, this is a very beautiful picture of unhappy numbers. Whatever the number on your screen, they are all unhappy because they form a cycle, and the cycle numbers are painted in red color. You see here. 20, 42, 145, 89, 50, whatever may be the number on your screen you are looking so far. If we adopt that process, then you will see that that goes to either 58 or 89 or 145 or 42 or 20 or 4 or 15. After coming to this number, this forms a cycle. So we are not getting 1 here. So this is a unhappy number. Okay. So I am switching all these things. Directly will go to our main topic. Okay. Yes. Before I want to go to my number sequence, as I said, that my number is actually balancing numbers. I want to say something about the balancing number today. But before that, some related sequences I must say. Okay, otherwise you will not understand this concept of this balancing number. Okay, so the Fibonacci number is a very well-known number sequence to everyone. Everybody know because it is a very celebrated number sequences invented by Leonardo of Pisa in 1202 in his book Liber Abaci. He actually posed a problem in order to invent this number, right? That problem was famous rabbit problem. So I will tell about this rabbit problem. You see the rabbit problem here, famous rabbit problem. You see the rabbit problem here. So this is the problem he posed. Suppose there are 2 newborn rabbits, one male and other is female. Question is, find the number of rabbits produced in a year if these are some conditions. In order to get the Fibonacci number, these are some conditions. What are the conditions? Each pair takes 1 month to become mature. Each pair of rabbits takes 1 month to become mature. Matured होने के लिए 1 महीना लेते हैं each pair. Each pair, another restriction is what? Another condition is what? Each pair must produce a mixed pair. This is also one condition. It is not necessary, but here, in order to get the Fibonacci sequence, this is the condition here. Each pair produce a mixed pair. That means one male and another one is female. And one most important thing, during this process, after 1 year, how many number of rabbit we will get? During this process, no rabbits die. Means all rabbits are immortal. So that is our condition. Okay. So these are the conditions posed by the famous mathematician Leonardo Pisa, better known as Fibonacci. Okay. Yes. So you see in the first month, in the first month, it is one pair. See the tick mark, one male and another one is female. It takes 1 month to become mature. That means suppose this one is January. So in the February month, this pair is matured now. So what is the number of pair in the second month, February month? It is still 1. Previously it was 1 and now it is still 1 because it will take 1 month to become mature. Okay. So after mature, gives rise to a bus. Okay. So they produced a mixed pair. Okay. So this pair produced a mixed pair here. So how many pairs in the third month? That is in March. We have 2 pairs. One is the original pair, that matured pair, and now a newborn baby pair, right? So again, you see in the month of April, what we'll get. This is the mature pair, comes to this one. This mature pair again produce a newborn pair. And this newborn pair takes 1 month to become mature. So now it is a mature pair. So how many pairs are in April? These are 3 pairs. So if you go like that, you will see that in the month of May, it becomes 5 pairs. So how we are getting? In the first month, we are getting 1. In the second month, we are getting 1. But in the third month onward, we are getting the sum of these previous 2 terms, that is 2. 2 plus 1 is 3. 3 plus 2 is 5. So in the month of June, how many will get? 5 plus 3, that becomes 8. Okay? Right. So this is actually the Fibonacci number. So Fibonacci numbers are what? The first Fibonacci number I am taking as 1. Second Fibonacci number as again 1. Third onwards, we are getting, third is F2 plus F1. Fourth is F3 plus F2 and so on. So in general, Fn is Fn minus 1 plus Fn minus 2. That is the sum of the previous term. Okay. So this is, if you are mathematics students, then you can easily understand that this is actually called the recurrence relation. So what is the meaning of recurrence relation? Recurrence relation for a sequence Fn, this one actually. Okay. So recurrence relation means for any sequence n, recurrence relation means its nth term, if it is expressed in terms of its previous term, then we say it is a recurrence relation. Like differential equation, a recurrence relation are sometimes called as difference equation. Difference equation. Okay. So like differential equation, difference equation is also homogeneous or non-homogeneous type. Okay. Homogeneous. This one is a homogeneous because this sequence, this recurrence relation contains, every terms of this sequence contain the terms of a sequence. suppose I add here n. So this last term does not contain the term of a sequence. So it is non-homogeneous. Because every term of that sequence, so that recurrence relation, contains a term of a sequence. Therefore, it is called a homogeneous recurrence relation. So I will not go to solve there are methods in order to solve the recurrence relation. I am not going to that. I am only concentrate to the homogeneous recurrence relation of this Fibonacci sequence. Okay. So am I audible? Am I still audible to everyone?
Yes, sir, you are audible, sir.
Okay, okay. Thank you, thank you, thank you. Okay. So, yes. So, this sequence Fn is equal to Fn minus 1 plus Fn minus 2 when n is greater than equal to, say, if I define F1 as 1, F2 as 1, then obviously n is greater than equal to 3. But sometimes what happens, you can start with 0 also. F0 is equal to 0. F1 is equal to 1. You can start with this also. These are called the initial conditions. So every recurrent sequence has an initial condition. So this is an initial condition. So if I start with F0 is equal to 0 and F1 is equal to 1, then n must be started 2 here. I request all of you to please unmute, please mute yourself. Disturbance is going on. Please mute yourself. Please mute yourself. Okay. So F0 is 0 and F1 is equal to 1. Right. So how to solve this one? If we solve this, Fn is equal to Fn minus 1 plus Fn minus 2, recurrence relation method, those who have studied in +3, that is discrete mathematics, you know that the auxiliary equation of this recurrence relation is some lambda square is equal to lambda plus 1. It is a quadratic equation and its solution is minus 1 plus root 5 divided 1 plus or minus root 5 divided by 2. Not minus 1. 1 plus or minus root 5 divided by 2. So the first root is 1 plus root 5 by 2. Another root is 1 minus root 5 by 2. And this 1 plus root 5 by 2 is called the golden ratio. And this has lot of application, friends. Lot of application and many research is going on this golden ratio. So this is the golden ratio. Fn. Why it is called golden ratio? Because this is actually a ratio of the Fibonacci numbers, consecutive Fibonacci numbers ratio. For example, I can say 1 by 1 is 1, 2 by 1 is 2, 3 by 2 is 1.5, 5 by 3 is 1.66 something, 8 by 5 gives us 1.667 something. So this is actually 1 plus root 5 by 2, the value. So Fn plus 1, the previous one, term with Fn. This Fn plus 1 by Fn tends to a number. This is the golden ratio. That's why it is called the golden ratio. And this is denoted by pi. And the value is 1.60 something. And this is 1 plus root 5 by 2. And it comes from the recurrence relation for Fibonacci sequence. Okay. So Fibonacci sequence, why this is important, that I don't want to tell because it appears in nature and it has a wide range of applications. It appears in nature, in flowers, many flowers. You can count the number of petals. You will see that Fibonacci sequence, and by Fibonacci food. These are all funny things that the number theory observed. That when you cut an apple, also you are getting 5. 5 is a Fibonacci number. Okay, in the shape of pineapple also, if you calculate the number of skulls, then you will find the Fibonacci sequence. And in the golden ratio, if we take the golden ratio and you will use that in order to paint or in order to construct a building, and you will find that look nice, because Mona Lisa painting, you know, that is the most beautiful paint in the world, and it is painted or using this golden ratio concept here. Okay. So now I am coming to the main topic. I will not take much time. Don't worry. I know my limitations, and I will start. I have already started this one 5:15, so I will get 45 minutes maybe. So 10 to 15 minutes I will over this one. Okay, I will over my talk. Okay. So my topic is balancing number and their related sequences and overview. So before I go for balancing number, I would like to define some terms which are used in this concept. One is called Diophantine equation. So what is a Diophantine equation? Number theory, those who have read number theory, Diophantine equation. So Diophantine equation means what? It is a equation whose solutions are integers only. Okay. So if we are finding the solution as only the integral value, only the integer, then that type of equations are called Diophantine equation. The famous Diophantine equation, you know, x to the power n plus y to the power n is equal to z to the power n. Fermat's last theorem that you know. So this is x to the power n plus y to the power n is equal to z to the power n. Has no solution when n is greater than equal to 3. It has a solution up to x square plus y square equal to z square, and this is the Pythagorean triplet, you know, x, y, z is the Pythagorean triplet. Okay. So this is the meaning of Diophantine equation. So what is a balancing number? Before I will go for the definition of balancing number, I want to ask some questions to you, please. You will not give the answer, you just see what are the questions I want to pose this one. These are some fascinating properties, well-known properties in natural numbers, right? So the sum of odd natural numbers, this is a high school things, you know. Sum of odd natural number is n square, whereas sum of even natural number is n into n plus 1, right? So my question is, this is actually for natural number. These are the property for natural numbers. So my question is there any other sequence an exists other than this natural number satisfy same type of result, that is a1 plus a3 up to a2 minus 1, odd term sum gives an square and even term sum gives an plus 1? That is my question. Please remember this one because I will give the answer of these questions after that. Okay. Right. Next question I want to pose. This is also high school standard question. A plus b into a minus b is a square minus b square. So my question again, is it possible for any real or complex sequence an satisfying the same type property? That is am plus n into a minus n is am square minus an square? That is my second question to you, friends. This is also high school level, trigonometric, de Moivre's theorem. Cos x plus I sin x, complex number, cos x plus I sin x whole to the power n is cos nx plus I sin n. Or in general, we can say cos mx plus I sin mx whole to the power n is cos mnx plus I sin mnx. So my question is again, friend, is it possible for any sequence an satisfying this de Moivre type property? That is am plus alpha bm whole to the power n equal to amn plus alpha bmn for some alpha. Okay, this is my question again. Okay, next question you see. trigonometric identity, everybody know sin x plus y is sin x into cos y plus cos x into sin y. Even if minus sin is also there, sin x into cos y minus cos x into sin x. So my question is it possible for any sequence an satisfying this type of property? Am plus n, am bn plus bm n. For some sequence bn related to n in some way, like cos y is related to sin y in some way. You know, cos square y is 1 minus sin square y. So cos y is related to sin y. In the same way, suppose we have a bn which is related to n, and my question is that type of sequence present here, satisfying this same type trigonometric type property? Okay, these are my questions. Okay, next. This is, you know, for Fibonacci sequence, this is true. This symbol is GCD, greatest common divisor. Fm, Fn bracket means the greatest common divisor of Fm and Fn is Fmn. You can verify. 813, greatest integer, GCD, is actually F GCD of 8.
Sir, sorry to say it's not audible.
Sir, your voice is not audible, sir. ନା ଅଛନ୍ତି ସାର୍। ଆପଣ ଅଛନ୍ତି ସାର୍? ହଁ ସାର୍, ଦେଖୁ ସାର୍। So it's right, sir. Sir. Sir, sir. Oh, sir. Yes, yes, sir. Yes, sir. No, sir. You're again, sir. ଆପଣ ପୁଣି ସାର୍ ବାହାରୁ ପଳେଇଛନ୍ତି ସାର୍। ନାଇଁ ସାର୍, ନାଇଁ। ନା ସ୍କ୍ରିନରେ ସାର୍ ଆପଣଙ୍କର ଉପର ବିଜୟ କୃଷ୍ଣ ଆପଣ ଅନମ୍ୟୁଟ୍ ହେଇକି ଅଛନ୍ତି ସାର୍। ଆସିଲେ ସାର୍, ଏବେ ଆସିଲେ ସାର୍।
अनम्यूट है ना देखो अनम्यूट है हाँ हाँ ठीक है शेयर कर स्क्रीन टा देखो कटि जाउची कहीं कौन नेट प्रॉब्लम हो स्क्रीन टा आसले कि देखले आसले स्क्रीन टा अच्छा ठीक है so now it is visible okay okay so am I audible to everyone नहीं अपना फोन रे कहउछी किंतु
ऑडिबल सर यू आर ऑडिबल सर
audible okay thank you so a balancing number satisfy all these properties so balancing numbers was invented by a nearby mathematician from NIT Rourkela Professor G.K. Panda who was my guide okay and his guide Professor Akrura Behera they have invented this number and believe me now friends these numbers are now many people from all over the world they are doing research in this particular number okay so I want to define this balancing number okay so the balancing number B and the balancer R are solutions of the Diophantine equation as I said the Diophantine equations means the solutions of that equations are integers only so this is the equation you see 1 plus 2 up to b minus 1 which is equal to b plus 1 plus b plus 2 up to b plus r so from this equation if we solve then we will get a pair that is b and r and this B is called the balancing number, and R is called the balancer corresponding to the balancing number B. For example, let us take B is 6. So from the definition, it is 1 plus 2 plus 3 plus 4 plus 5. Sorry, plus 5. 6 minus 1 is 5, which is equal to B is 6. 6 plus 1 plus, you see, what is the sum of this number? Is 15. And this is 6 plus 1 is 7. And next is 6 plus 2. That is 6 plus 1 is 7 plus 8 gives us 15. So both are balanced now. So the first balancing number according to this definition is 6. With balancer 6 plus 2 R. That means balancer R. This is the first pair. 6 is the first balancing number with balancer 2. Okay, according to this definition, because 1 plus 2 plus 3 up to 5, according to this definition, up to 5 is equal to 6 plus 1 plus 6 plus 2, that is 15 and 15. Now it is balanced, equation balance. So 6 is the balancing number with balancer 2, correct? Now, like Fibonacci number, balancing number are not near to each other. It is far away from each other. The second balancing number is 35, friends. That means if we verify 1 plus 2 up to 34, I'm sorry, 35 minus 1 is 34, which is equal to 35 plus 1 plus 35 plus 2 up to, you can verify this one, 35 plus 14. I remember, that's why I'm writing all these things. Okay. So next balancing number is 34 with balancer 14. The first balancing number according to the definition is 6 with balancer 2. The next one is 35 with balancer 14. The next one is 204 with balancer 84 and so on. So these are some examples of balancing numbers. Okay. This balancing numbers come from the definition directly. That is the solution of this Lafontaine equation. But there is a testing of balancing numbers. Okay. How we know that any natural number is a balancing number? So any natural number is a balancing number if and only if n square is a triangular number. So if you remember the definition that I have already told you in the first part of this talk, that n is a triangular number if 8n plus 1 is a perfect square. Now n is a balancing number if 8n square plus 1 is a perfect square. 8n square plus 1 is a perfect square. It means that n square is a triangular number. So n is a balancing number if and only if n square is a triangular number. This is the definition now. So from this definition, you can verify, because as I told, 6 is the first balancing number, 35 is the second. So you can verify that 8 into 6 square plus 1 is 17 square, it's a perfect square. 8 into 35 square plus 1 is 99 square. 8 into 204 square plus 1 is 517 square, and so on. Okay, so these are 6, 35, 204. They are actually comes from the definition, and also from this definition we verified already. But if we put in place of n 0, 8 into 0 square plus 1 is 1. 1 is a perfect square. If we put in place of n 1, 8 into 1 square plus 1 is 9, is a perfect square. So 0 and 1, they are also treated to be balancing numbers, though these few numbers are not directly come from the original definition, right? So original definition ru a number asi nahi, but this number comes from this definition 8n square plus 1. So that's why we are taking the first balancing number as B0, say it is 0, B1 as 1, B2 as 6, B3 as 35, B4 as 204, and so on. These are actually balancing number sequence. Like Fibonacci number, balancing numbers are also has some recurrence relation. So what is the recurrence relation for balancing number? If you look it, that has been already found in that paper. So I'm not going to prove this one. Just I am writing the recurrence sequence. That is bn plus 1 is equal to 6bn minus bn minus 1. This is the recurrence relation for balancing sequence with initial value b1 is 1 and b2 is 6. If we put here, we'll generate all the balancing sequence. Okay. Lots of research are going on now. As I told that it isn't just an overview of balancing number. Only the definition and some example I want to tell. Okay. And this is nothing else. So if we go for the research, you can find from the Google, directly write down Google balancing number, you will find many papers that nowadays also the people are doing. Okay. Right. So, right. Now, for each balancing number, so how much time I have now? 5 minutes maybe. Dr. Panda? Dr. Panda, can you hear me? Dr. Panda?
Sir?
Can you hear me? Yes.
Yes, sir. I'm hearing, sir.
Okay. So, how much time I have now?
So you have another 7 minutes, sir.
5 to 7 minutes. Thank you. Thank you. I will complete this one within that. Okay. So now come to this one again. Okay. So you see the next balancing number is 3bn plus 8bn square plus 1 root over, and the previous one is 3bn minus 8bn square plus 1 root over. So for each balancing number, we have a next balancing number and previous balancing number. You can verify that. Suppose I take B2 is 6, then B3 is 35 here. This is the next one. And the previous one is 1 here. So you can verify for 35 also. But this 8bn square plus 1 also generate a sequence, and I name it as Cn. And this is called the Lucas balancing number. Okay. So for example, if I say n is equal to 1, so 8 into 1 square plus 1 is 9, root over is 3, positive square root. So for B1, 1, C1 is 3. For B2, 6, C2 is 17. So 1, 6, 35 is balancing sequence, whereas 3 is 17, next one is 99. These are the Lucas balancing sequence. So why we name this one as Lucas balancing sequence? Because friends, as you know that Fibonacci numbers and Lucas numbers are well connected. So Lucas numbers and Fibonacci numbers, the way they are connected, in the similar way, our Lucas balancing numbers and the balancing number are connected. That's why we name it as, okay. So I think I should stop here because yes, can you hear me? So any questions you have regarding balancing sequence, or so there are many things, but I don't have time to explain this one. I'm sorry. So I should stop here because I have also another assignment now. Okay. Yeah. I want to tell quickly that our balancing sequence satisfy the questions I have raised. That is, m plus n into m minus n is m square minus n square, and also the sum of odd natural number is n square, whereas sum of even natural number is n into n plus 1. So our balancing sequence satisfy the same type as that of natural number. You see, odd balancing number of sum. You mark it. Odd balancing number sum is bn square. Even balancing sum is bn in bn plus 1. Fibonacci numbers re ebhaliya property nahi. So these are some more beautiful property than Fibonacci sequence. So whatever property So am I audible now? Hello? Dr. Pandav, am I audible now? Hello, Dr. Pandav, am I audible?
Yes, Professor Rai, you are audible.
So I am audible. So
Yes,
my talk is already over. Okay. Hello. Yeah, my talk is over already. So internet problem, I think so. Yes, yes. Dr. Arvind Pandav. Dr. Pandav.
sir, audible, sir.
Yes, my talk is already over.
Okay, okay, sir.
Okay. So any questions, friends? If you have some questions, you can ask me. Dr. Pandav? Dr. Pandav? Hello, Dr. Pandav. No one is responding. So any participants? Am I audible to you?
Sir, audible, sir.
Okay, but where is Dr. Pandav? Because I have already completed my talk.
Sir, there is some network problem, sir. Server is
Oh,
slow.
okay.
Okay, sir. Please bear it, sir.
Okay, sure. Because my talk is already over.
Okay, sir.
Sir. ସେ ମୋର ସରିଗଲାଣି ଟକଟା ତ ଆପଣ ହଉ ମୁଁ ଲିଭ୍ କରିଯିବି ତ ହଉ ଥ୍ୟାଙ୍କ ୟୁ ମୁଁ କହିବି ହଁ ଠିକ ଅଛି ଆସନ୍ତୁ ମୁଁ ଅଛି So, dear participants, if you have any questions, you can ask me now.
Dear participants, it is an internet issue, and sorry for the inconvenience regarding this matter. And now the thing is that Professor Roy is asking, is there any question regarding balancing number? You may ask.
Good afternoon to all the participants, and Dr. Manaskan Naik, the host of this webinar. Our resource person has already delivered his beautiful lecture. Now, if any participant has any question, they can ask questions directly to our resource person. So, जदि participant को कौन सी question था, इस समय question directly पचाई पांति. If they want, they can also write questions on the chat box. Prasanta sir, please on your video because we want to take some photos.
Sorry. Actually, my internet is very slow, so that's why.
Okay. Yes, sir. Yes,
okay.
Okay, sir.
So.
Sir, I think there is not any questions regarding this webinar. So students, there I don't see any question in the chat box, or and there's not anyone who is asking questions. So
okay,
we'll
no
go
problem.
Forward, sir. Okay. Now I request Dr. Sunil Kumar Pradhan, the resource for the IQAC coordinator of Pattamundai College, please take over the charge. Yes.
Thank you, Dr. Manas Kumar Naik. And now, thank you, Professor Rai, for your nice presentation and a beautiful talk. I hope the students will be benefited from your talk. Our second speaker is Honorable Dr. Bijoy Krishna Debnath, Assistant Professor of Mathematics, Tezpur University, Assam. And he will be talking on the topic, a talk on some inventory modeling. The next speaker of our webinar is Dr. Bijoy Krishna Debnath, Assistant Professor of Mathematics, Tezpur University, Assam. And he is joining us from a distant corner of India, that is from Assam. We welcome Dr. Bijoy Krishna Debnath to our webinar. Please, sir, deliver your talk.
So, good afternoon to all. I hope I am audible.
Yes, you are audible.
Okay, so there might be some internet issue that I have seen throughout this webinar, so I might also face. So I don't know. Let's see. And at the outset, I would like to thank the principal sir and Professor Pandab sir to invite me for this beautiful webinar. And also, I want to thank all the faculties of Pattamundai College to organize this webinar. So let me share my screen. Okay, this screen is visible.
Your screen is visible.
Okay. So welcome participants. Let me stop video of my screen. Okay. So Today I will deliver a talk on some inventory modeling. But prior to that, I have assumed that all of you have studied the linear programming programs, simplex methods, right? Not some non-linear. These are all linear programming problems, right? All of you have studied now in your BSc times. Many of you from BSc might, some of you from MSc or research scholar, I suppose. So these linear programming problems and non-linear programming problems, these all are parts of operation research. So basically, what do you mean by operation research? So operation research is basically a systematic and analytic approach to make some decision, right? Suppose we have some problem with some variables and some objective functions that need to be maximized or minimized subject to some constant, right? So these operation research are not new concepts. Okay, this has been started way back from the second world war, when these military operations were going on from. Hello, I'm audible now?
Yes, 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 sir, audible.
Okay. So like these military operations were going on from Britain to different countries, right? So they have to keep the medicines and some volatile things to transform from Britain to some other countries to operate the this in war, na? So from that time this operation research came, that how to should we take the decisions on certain issues, so that our human resource should be optimized. We should not use so much of so much of human resource to not like operate correctly, right? So basically operation research is a systematic and analytic approach in decision making and problem solving. Okay, so it is characterized as a application of scientific method, techniques and tools to problems involving in operations of a system, like uh, maximization, minimization, constant optimization, etc. Okay, so basically, let me start with this inventory modeling. Now, what do you mean by inventory? Let's first understand. So, inventory is a well-known concept in business management. You know, like for managing the stock, na, when some company produce some items, right? You may take on any medicine company, cloth industry, or any kind of industry. They are producing some item, right? That item needs to be stocked somewhere, like in warehouse. So this stock or this inventory, this is called inventory actually. Basically, the stock is called inventory. Now this you cannot hold too much of inventory, right, in certain warehouse, because this also costs involving to hold these items, right? These calls are called holding cost, right? And there are three layers of supply chain. One is called the supplier, who actually supplier or wholesaler or manufacturer, who basically produce the items. Then they sell to the retailer, who basically bought items from the supplier, and they sell to the customer. So there are basically three layers. One is supplier, one is retailer, one is customer. So basically, in each of these process, this inventory build up, right? Suppose this wholesaler or manufacturer produce some items, so they have to keep their items somewhere, na, that warehouse. So that is their inventory. Then the retailer bought those items to his stores, right? So you can imagine of any store, multi-item stores, like Big Bazaar, this Walmart. These are all stores, retail stores, right? They are supplier basically. They are the middle person. So they store some items in their shelf, right? And they sell item to the customer. So customers are the end users. Okay, middlemen are the like Walmart, Big Bazaars. These are the middlemen, that is called retailer, and supplier is like from who supplies, right? So in retailer may have different kind of items, right? But supplier has only one kind of item who is there basically produce or manufacturing. Okay. So basically this is the actually inventory, and why this modeling is needed. Actually, like in business management, they are using so much of money in HR section, human research section. So the big companies, they hire some inventory practitioners to make some decisions on how much inventory should you build up, or how much inventory should you have in your store, so that your holding cost also optimize, your ordering cost also optimize, all the costs are optimized, and you get some maximum profit, inculcating some minimum cost, right? So these are the basically inventory modeling. And in mathematics peoples are like, they're involved in anywhere, right? So they have build up this inventory modeling in mathematical form, and mathematically the concept that we know from our basic concepts, like if we want to maximize something, how we maximize? First derivative equal to 0, and at that point we will calculate the second derivative, and if second derivative is less than 0, we get the maximum point, right? So, and if second derivative is greater than 0, we get the minimum point, right? So these concepts are used in this operation research and inventory modeling, and develop different kind of models. So here basically inventory models are classified into two types. One is called economic order quantity, another is called economic production quantity model, right? So in economic order quantity also there are two types. Economic order quantity model without shortage, and economic order quantity model with shortage. And also economic production quantity models are classified in two types: with shortage, without shortage, right? Next, if time permits, I will also discuss on this multi-item inventory control model with constraint. Okay, and another is with all quantity discount model. Let's see how far we can go. Okay, so basically these models, the general models, are classified into three types. One is like iconic model, analog model, and mathematical model. And we just only discuss on these mathematical models, and you know that mathematical models are again classified in two types: static and dynamic. Static means it does not change over time, and dynamic means it change over time. And both of these type have this linear and non-linear uh, problems. Like, as you know, these simplex methods, linear programming problem, these are all linear, and these some are also non-linear programming problems are also there, like quadratic programming, integer programming. These are all non-linear programming, right? So these are there. And then this, how we can define these models. These parameters can be deterministic, that means known to us always, and might be probabilistic, that means that follows some rule with known mean and standard deviation, right? So in comes to the solution point, the solution might be of two types. One is called analytic solution, one is called simulation solution. So what do you mean by analytic solution? Analytic solution means this problem can be solved analytically and we get an exact solution, like we did for LPP, simplex, right? But you know that many of the nonlinear programming problem cannot be solved all the times, right? There are some rules only, like Lagrange multiplier rules, and then min max optimization problems, integer programming problems. This type of certain problems can be solved, right, analytically, not all, right? And some other problems are called simulation type of problem, in which we with the data, with the predefined data, we predict something. We have certain data. Suppose for you may think weather forecasting now. So we have the previous 2 month, 3 month data of weather, and and the previous year data also. And upon this, we have to predict something about that situation, how tomorrow will be, how tomorrow will be look like. Like this is called the simulation problems. Okay. Am I audible? So ऐसे बीच बीच में बोलते रहूंगा. Am I audible? क्योंकि like this is like something like that I am talking with my computer also.
Yes, sir, you are audible. You are audible, sir.
Okay, okay, okay. So next, move on to this slide. So you know that real life, how modeling is done. This chart is very important. Suppose you have some real life problem, right? So real life problem, you cannot take all the phenomena of real life into your model. Otherwise, your model will be so much of complexity. Complexity comes. So you just choose. You just choose some particular aspect of reality which needs attention, and you have to define your problem, right? Then you have to define mathematically the model. Like you have to, if some data are available, collect those data. If there are some relationships available among the variables, parameters of the system, and then you'd have to define the objective function, right? Then this objective function need to be solved with some suitable operations techniques to get the solution in terms of decision variable. Then you have to again re-verify whether this testing the model, that means if the model and solution follow the practical rules or not. If you define some model and your parameters or the variables does not fit the natural phenomena, because these inventory models or any kind of mathematical modeling problems are basically real life problem that should follow some real life applications, right? So that should follow some real life uh, properties that needs you need to check it. Okay, if your model satisfy, well and good. If not, you have to modify the model, right? And solve again with some changes of parameters, right? So this way. And you have to also show these applications, right? If you define some model, or if you optimize a model, so in reviewer always asks there, what is the applicability of your model, where we should apply this model, right? Because if you are working in any of the mathematical modeling field, your reviewer always asks you, or company always asks you, how we can implement this to the end customer, right? Okay, so you have to must show some implementation, okay, on the result. So coming to this definition of this inventory model. So inventory model is a mathematical model that helps a business in determining the optimal level of inventory that should be maintained in a production process, managing frequency of ordering, deciding on quantity of goods or raw materials to be stored. Okay, so basic inventory models are economic order quantity and economic production quantity. Now I will discuss what do you mean by economic order quantity. Basically, economic order quantity, you just see from this graph that here that means you think of you are suppose a businessman, okay? You are suppose a businessman, you get some quantity directly from the manufacturer. So that is called order quantity, order size. That means you suppose you are selling of a rice company, working on a rice company. So suppose you are ordering 100 bags of rice, right? Or you can if you are ordering cloth, you are working in cloth industry, or you are businessman of cloth. So suppose you are ordering 1 lakh piece of certain type of uh, cloth. So this is like a order quantity. So that means the supplier gives you an order quantity to the retailer, okay, directly. So this is like this amount is Q. This amount is Q, and that is called order size or inventory level. And suppose you think of a shop in which you have 100 bag of rice, and the customer comes to your shop, and uh, they are demanding of like 2 bags of rice, three bag of rice, okay, at a time, or 4 bags of rice. So these are called demand. These are called demand of the customer, right? So you this quantity, this or this is called order level or inventory level Q, and this line is like, this line is called demand line. Okay, here everything is constant, means this Q is constant, that means how much of order quantity we should take, that is constant. This demand is also constant, that means if you take any constant time now, so the consumption from the system is always same. That means five bag of rice in every 1 day. If you consider your time period as suppose 10 days, so you suppose order 50 bag of rice. You suppose order 50 bag of rice, and your per day order consumption is 10 unit of bag, right? So 10 day, 10 unit consumption for 1 day. So how much day it will go? It will go for 5 days now, because you have bought 50 units, right? So this is suppose Q and Q. So Q equal to dt. So T is the what? T is the time period. This is for one cycle. And again, here you order another order quantity of size Q. So here it is assumed as the replacement is instantaneous. That means whenever you order another Q quantity, you get it directly, and your like warehouse raised by this Q in it. Okay, and again there is consumptions, and at the time 2t it finished. Again you get, again if consumption finished, so like this way. So this is the basic fundamental model that is formulated by Harris, F.W. Harris, way back in 1923, almost 100 years back. Now these models has changed and modified in many ways. In many ways it has modified. So you have to think of this. Okay, and like I will show you some of the modifications, okay, of these models. So like if I say what are the, okay, so now for a single item, so this is a single item model and constant demand. So basically total annual cost consists of two parameters. That means you have to order some quantity now, so that means you have to pay some ordering cost for that, is not it? And you have, suppose you have arrived some quantity, order quantity, so you have to hold them now. So for that you have to pay some holding cost. So that is called annual holding cost. So your inventory system consists of two costs only, ordering cost and holding cost, right? No other cost is involved. That means ordering cost involves ordering of an item and get received. All the main labor cost, all the costs are involved in ordering cost, and holding cost is associated with hold this inventory. Okay, now how we calculate this ordering cost? Basically number of orders placed per order per year, a number of orders placed per year into ordering cost per year per order. So हर order में कितना cost देना पड़ता है और हमने कितना order place किया है एक साल में. Okay, this is ordering cost calculation for every year. Okay, and how we calculate this holding cost? That average holding level, because this consumption is going on now. So what is the average holding that is that you kept in your warehouse? That is average holding cost. So average inventory level into holding cost per unit per year. Okay, so एक यूनिट को एक साल के लिए होल्ड करने के लिए कितना पैसा तुम्हें देना पड़ता है इनटू एवरेज इन्वेंटरी लेवल, मतलब तुम्हारा इन्वेंटरी एवरेज इन्वेंटरी लेवल कितना है. तो नाउ हाउ वी कैलकुलेट दिस एवरेज इन्वेंटरी लेवल? सो योर मिनिमम इन्वेंटरी प्लस मैक्सिमम इन्वेंटरी डिवाइडेड बाय 2, और होल्डिंग कॉस्ट पर ईयर पर यूनिट के लिए हमने CH पकड़ लिया, प्लस नंबर ऑफ ऑर्डर, कितना ऑर्डर देना पड़ा. क्योंकि देखो तो लाइक your per year consumption might be your per year for entire cycle, for entire cycle your order demand may be 1000 units, and every time you are getting 100 units, right? So how many times you have to pay the order? 1000 divided by 100, that means 10 times, right? So this is the number of orders into ordering cost, that is C naught. Okay. Now if your minimum inventory level is 0 and maximum inventory level is Q, so holding cost will be Q half into Q into CH. That means Q by 2 into CH plus D by Q into C naught. That is your total variable cost. These two are variable. That means this depends on this Q. No other cost is depends on Q, but these two costs are depends on Q only, right? Now you think that where should we, our graph maximize? Because this cost, we should minimize our cost, okay, to get the maximum profit. Now if you think of this graph, this Q is order quantity. So if you order a large quantity at a time, then you may get some discount. Also, that means, you know, from your practical experience, that if you order for 100, if you order for 10 units, we get big amount. We have to pay big amount. If you order for 100 unit, we have to pay less, right? If we order for 1,000 unit, then we have to pay more less, right? So that means if you this order quantity, when this order quantity is increasing, our annual ordering cost is also decreasing, right, with time. And like now you have this order, so you have to place somewhere, right? You have to hold this in inventory. So that means when this order quantity increases, your carrying cost also increases, na, because you have to pay some money for holding this inventory, na. So carrying cost is also carrying cost is also increasing. And remember, this carrying cost and holding cost are same. Carrying cost and holding cost are same, right? So uh, the point at which these two costs are cut, na, this is the optimal point. Because at this point, if you like, if you for each of this point, if you calculate the total annual cost, na, if you add these two, you will get the minimum value at this point. Although the graph is not fitted, but you think, na, if you add these two point, so because this point, this is like double of these two, and all the other points are bigger than this. So this Q star is the optimal point, optimal order quantity. So this is like a trade-off, or the trade-off or payoff in between ordering cost and holding cost, and we get the optimal value at the point Q star. Also, this calculation can be done by this derivative test. If you first see, we have to equal these two, and we get the optimal Q star, and this is wrote under twice d C naught by CH, and that is called optimal economic order quantity, right? So what is the value of this optimal order quantity? Wrote under twice d C naught by CH. So D is the annual demand quantity, C naught is the ordering cost, and CH is the holding cost. Okay, if you know this annual demand of some company, if you know the ordering cost per order, if you know the annual holding cost of certain company, then you can easily calculate the optimal order quantity that is required, or that is to be maintained by the company to minimize his cost or maximize his profit, right? And as I said, this Q star also obtained from, if you first derivative with respect to Q equal to 0, then you get this Q star value, and at this Q star, if you check this double derivative, okay, that will be greater than 0. That will be greater than 0. Okay, this is simple homework for you. So you see this example. Okay, so here annual consumption of a company is 10,000 units. So our D is 10,000, right? Okay, and cost to place an order is rupees 300. That means ordering cost is 300, right? So this holding cost is given in terms of like purchasing cost. That means if purchasing cost is 20 rupees per unit, then you have to pay 20% of the rupees 20%. 20% of rupees 20 for holding. Okay, that means what is the value of CH? 20 into 20 by 100. So that means you get 1224 into 0.74 units. That is your optimal order quantity. And if you put this optimal order quantity value here, you get the total cost. But here you remember I have added some extra term now, that is called the purchasing cost. That is called purchasing cost, that is required to purchase D amount, because C is the cost, purchasing cost, and how many amount, how many item you have bought, D in it. So total cost is DC. Since this term does not contain any Q, that is why this is not comes under total variable cost, but it will come under total cost. Understood? It will come under total cost, but it will not come under total variable cost because this Q star is not there. So if you put all the values, you get. Now for this problem, you get the optimal order quantity and total cost. Okay. Okay. Now move on to another model, that is economic order quantity model with shortage. Okay. So at this point, I have to again ask, am I audible? Any participant?
You're audible. You're audible.
Okay. Okay. So here you see that our optimal order quantity is Q, and that is means what is the situation for this model? So the situation is like that you have ordered some quantity. Suppose in your shop you have 100 bag of rice, right? In your shop you have 100 bag of rice. So you expected that your consumption will be finished by 10 days, right? But what happened, due to certain extra demand in the system, all the items are finished by 8 days. So you have you will only get the replacement after 10 days only. Now what happened after 2 days? Because you are a well-known businessman, customer will come to your shop and ask for his item, but you cannot deliver, right? So here in this model, we also consider such situation. This is called the shortage. This is called the shortage. That means the shortage amount, average shortage amount into cost, because this is also lost now. This will also lost some goodwill loss of the businessman, because if some customer come to your shop and you cannot deliver his requirement, that means he might not be happy with you, so your goodwill also lost. So this type of cost called shortage cost or back ordering cost. Okay. So you have this inventory level Q and shortage level is S. So positive inventory is Q minus S. Okay, this positive inventory vanish by the time T1 and started the negative inventory, and it goes up, it lasts up to T2. And at the point T2, you receive your replenishment order quantity, and it again raised by this Q units. Okay, and the cycles goes on. Okay. You understood the situation, and total time is T. So what you can say, T equal to T1 plus T2, T equal to T1 plus T2, and you know Q equal to DT, because our optimal order quantity Q that needs to be finished by the time T, means total time. So Q equal to DT, and T1 equal to Q minus S by D. T1 equal to Q minus S by D. Then T2 equal to S by D. Okay. Then what are the variable cost involved? That is ordering cost, holding cost, and shortage cost. Ordering cost, holding cost, and shortage cost. Okay. So ordering cost, basically, as I said, a number of order placed per year into ordering cost per order. So what is the number of orders? D by Q. And what is the cost? C naught. So D by Q into C naught. And what is the holding cost? Holding cost is basically average inventory level into holding cost per unit per year. Okay. So what is the average inventory? Because holding cost will be this for this much, na? Because this much of units you have, because this is negative. So what is the minimum? 0, maximum is q minus s divided by 2 into time. Time is t1 divided by total time. Total time is, you have to consider, that is t, small t. So q 0 plus q minus s whole bracket into t1 by 2t into ch. So if you put the value of t1 and t from above, you get this value q minus s whole square by twice q into ch. Okay, this is the holding cost. Okay, now how we calculate the shortage cost? That is average shortage level into shortage cost per unit time. So average shortage level, again shortage is there in this situation. So minimum is 0, maximum is s. 0 plus s by 2 for how much time? T2 time divided by total time is t. Divided by total time is t. So s t2 by 2t into shortage cost is cs. So if you put the value of t2 and t, what you get? S squared by twice q cs. Okay. Now here the variable is two variable. One is we have to optimize the optimal order quantity, and also we have to optimize this maximum shortage level s. Okay, that means you can see here q, we have to find out q star and f star. Okay, so here you can use by two ways. One is partial differentiation method using Hessian matrix. Hessian matrix, you know how to optimize two variable. Okay, so first you differentiating total variable cost with respect to q equal to 0, then with respect to s equal to 0, and using the Hessian matrix, you should be have some positive definite matrix to get the minimum value of q star and s star. And with this q star and s star, we get the total variable cost. And remember, in total variable cost, we have added this purchasing cost also. Okay, which I have not shown here. So these are available in any book you may refer to. Okay, so this is an example of such model. So here you can see our demand is 200 units per day, in which holding cost is 2 rupees 2 per unit. Okay, holding cost is rupees 2 per unit, and ordering cost is rupees 50, and shortage cost is rupees 10. That means if you don't deliver an item, you have to pay goodwill loss as rupees 10. So you get the optimal value of q star, that is root under twice d c naught into ch plus ch by ch into cs. If you put all the values here, you get 110 units. Okay, and you also can find out this reorder cycle period t, that is your q star by d. Okay, that is q star you get, and you put the value, you get the half days. Okay, now coming to this another concept, that is called economic production quantity. So economic production quantity you can refer through two ways. One is that, you know, the manufacturer produce some items. So manufacturer producing and delivered to you, and that means not like a batch. In order quantity, manufacturing produce and provide you as a batch, right? But here what is happening, that manufacturing is producing and simultaneously distributing to you. Okay, so if there is no demand, then the graph should be raised by this way, this dotted line. But since production and demand is going on simultaneously, so your curve should not raise that much, it is down by this point. And at the point of TP, you get the maximum production level, maximum inventory level, and at that time your production is stopped, right? At this point your production is stopped and only demand is there. Only demand is there, so demand is D. Okay, and you have this time TD. After TD, your demand becomes 0, and again you got another lot, and it is raised by at the rate of P minus D, and maximize at this point. Again only demand is there. Okay, So your total time is capital T, which is consist of TP plus TD. Okay, and your maximum inventory Imax is P minus D. Imax is P minus D, I mean is 0. Okay, so as said, so like okay. Okay, so this during this production rate TP, the inventory increase at a rate of P and simultaneously decrease at the rate of P. So therefore, the average inventory level is what? Average inventory level 0, minimum, maximum is P minus D divided by 2 into for how much time? TP. So TP is what? TP is Q by T, right? So if you put it and multiply it, what you get? Q by 2 into 1 minus D by P. Okay, then you calculate this carrying cost. As I said, average holding cost into cost. Then setup cost is, you know, number of orders into cost. Okay, then you find out this total variable cost, which is this average holding cost into holding cost plus number of orders into cost. Okay, now you have to maximize again. So you equal both of them, and from that you get the Q star. Else you can do this first derivative equal to 0. You also get this point, and you can check that second derivative is greater than 0. Okay, so this is the optimal Q star for economic production quantity model, right? Now you can see how these two, how we can go to economic order quantity model from economic production quantity model. That means here if P tends to infinity now, if P tends to infinity, this term becomes 0. So this will be like wrote under twice D C naught by CH, which is same as economic order quantity model. So that means when our production is infinite, or like you can say that the production is infinite means the manufacturing gives you certain amount directly to the customer, then this P tends to infinity, right? In this case, this Q star becomes this EPQ Q star becomes EOQ Q star, right? So here is an example. I have given this PDF to the organizer, so you may go through. This is simple example, so I should not tell this again. So here another model in EPQ model with shortage. EPQ model with shortage. That means you can see here. The inventory build up at the rate of P minus D for the time T1, and then this demand comes. Okay, but as I said already, that means you have 10 days. After 10 days only you can replace. Your replenish will arrive, and your cycle will be boost up. But your inventory finished up by 8 days. So for 2 days you have to bear this loss. That means shortage lost. Okay, so here for T1 production for production and consumption, this inventory build up at the rate of P minus D, and at T1 it goes the maximum level, Imax level, and then there is demand, and for demand T2 your inventory becomes 0. Still you get the demand, and your demand gets the maximum level IB for after time T3, and at the level T3 you receive the order. So this is your maximum shortage level, and you receive the order. So you filled up this first you filled up these shortage levels, and then your positive inventory will be built up, and then this cycle continues. Okay, in which the total cycle time is capital T. So capital T is equal to T1 plus T2 plus T3 plus T4. Okay. So in this case, our optimal production quantity is root under twice D C naught into CH plus CS by CH into CS of 1 minus D by P. And here also we can go, if we divide this term now, 1 plus CH by CS. That means if shortage tends to infinity, na, if there is no shortage, if there is no shortage, if there is no shortage, then this model goes to this previous model. And if we also along this, if p tends to infinity, if p tends to infinity, then this EPQ model goes to EOQ model. Okay, so here is an example. Now let us move on to the next constraint model. That means here we have assumed multi-item. Here we have assumed multi-item. So suppose there are n number of item. Total number of item is n number of item, which is controlled simultaneously, and total floor area is Fi for each of the item. Okay, for each item I, floor area is Fi. Okay, and warehouse space is W. Warehouse space limited to store all the items in the inventory is W. Okay, and for each of the item demand is Di. Okay, order quantity for each item is Qi. Okay, so here you see that for each of the item floor area is Fi. So what is the total floor area for the Qi item? Fi Qi, and how many items are the n items? So this total sum, and that total floor area should not be greater than this W, because W is what? The warehouse space limit, right? That means you may think of a situation in which you have suppose five items, right? So for 5 items. So for each of these items, you have different floor area, right? So for first item, you have this F1, right? So first and F1 Q1 is the total floor area for first item. So for similarly for 5 items, you have F1 Q1 plus F2 Q2 up to F5 Q5. Then this total sum should not exceed in W, right? So this, and that is less than equal to W. And total variable inventory cost, right? So here you have the only ordering cost and holding cost, as you already know how to calculate this, but here will be summation for multi-item. Okay, since there are n number of items, so this summation run from I equal to 1 to n. Okay, clear? Now this has to maximum, subject to this floor area. This needs to be minimized, subject to this constraint, this floor area. Now this is like how we can do it. We'll use by using the Lagrange multiplier lambda. Lagrange multiplier lambda. So how we calculate this Lagrange multiplier? So you know that first function plus lambda into second function. That means this less than equal to 0 type first we have to take. So this first function plus lambda into gx. Okay, gx is summation fi qi minus w. The necessary condition is that this partial differentiation with respect to this qi should be equal to 0. Okay, and from then we have to find out this qi star equal to root under twice di coi by this. Okay, this is same, just only yeah, for multi-item there is I and one lambda is extra. Now you see that here, although all these are known, di is known, coi is known, chi is known, fi is also known, but lambda don't know, na? So based on this lambda we will get this qi star, is not it? Based on this lambda we will get this qi star. Now how we find out this lambda? How we find out this lambda? So there is some algorithm to find out this lambda. So because lambda is any constant, so first we choose that lambda equal to 1, and compute this EOQ for each item separately. That means QI star. Okay. Now if this QI star satisfies the condition of total storage space, for lambda equal to 1, if this summation fi QI star less than equal to W, okay, so then our lambda equal to 1 will be solution. If not, we have to increase the value of lambda, and we should increase the value of lambda to the maximum value in such a way that this condition, this summation fi qi should be less than equal to W. Okay, you may properly understood from this problem example. So you have three items now, 1, 2, 3, and this demand rate is there, purchase procurement cost is there, cost per unit is there, floor place is there. So for lambda equal to 1, you find out this Q1 star. So Q1 star is 542. Okay. Similarly, you find out this Q2 star, Q3 star, and you calculate this total storage space, and you will see that 1078. But you see that your total floor area is 650. Total floor area is 650, but you get with this lambda equal to 1, we get the 1078. So this cannot be your optimal value, right? This cannot be your optimal value. So you have to increase the value of lambda, because you see that lambda is in the denominator, right? Lambda is in the denominator. So if you increase the value of lambda, you will get minimum value of Q star, because you need to reduce the Q star. So you see that for lambda equal to 5, if we get Q1 star equal to this, Q2 star equal to this, Q3 star equal to this, and the corresponding total storage space required becomes 668.3. Still, it is greater than 650. Still, it is greater than 650. So you have to increase more. This is trial and error method. Okay, this is trial and error method. So if we take lambda equal to 5.4, then our total storage space become 449.6. That is almost near to 650. Okay, so if one can still further modify this lambda, but here for the time being, I have chosen lambda equal to 5.4 to get the optimal value of Q star. That means optimal item quantity for first one, second one, and third one. Okay, and this is the, I think, last model, EOQ model for quantity discount. So you know that if you buy, suppose 0 to B1 unit, you get some little high price C1. If you buy more than that, up to B2, then you will get some less amount or in ordering cost. And if you buy still more than that order quantity, then you will get some more than less of that amount that you previously paid for the ordering cost. So here discount price is applicable. So all unit is purchase. If there are several price breaks, say B1, B2, BI, and the order quantity Q lies in the discount interval, say BI minus 1 to BI, then the price also reduce. Okay, this is the concept. And for that, total annual inventory cost for discount schedule with these price breaks are basically purchasing cost, because here we are only considering the total cost, okay, for each of these items. That is consist of purchase cost, ordering cost, holding cost. So purchase cost, how we calculate? D into CI for IR item. Ordering cost is number of order, that is D by Q into C naught, and holding cost average. So this will be Q by 2. Sorry, this printing mistake. This is Q by 2 CH. Okay, and this CH is how we calculate this CH. CH is R times. That means some percentage of the purchasing cost. That is CI. Okay, some amount, some percentage, like 20% of purchasing cost to ₹20. Okay. So from this we can calculate this Q star by using first derivative equal to 0. So this is Q star equal to root under twice this C naught by Ci into R. Okay, so how we find out this solution actually, because the solution depends on this, because this is not a continuous function. This is not a continuous function that you can use this derivative, right? So you have to give some discrete algorithm to solve this model. So what is a discrete algorithm? You see that if you purchase the 0 to B1 quantity, you have to pay this price C1, and if you purchase this B1 after B1 quantity, you have to give another price break. Okay, obviously C2 will be less than C1. So you will betterly see this example. I will show you this example. So here annual demand is 10,000 units. ordering cost is rupees 5 on R 10% of price of the item. Okay, 10% of the you have to pay of the price purchasing cost. So if you buy up to 20 units, you have to pay 100 rupees per 100 rupees price per unit. If you buy more than 200 units, you have to pay 95 rupees. Okay, so how we calculate the optimal order quantity Q star? So obviously root under twice it is C naught by C2R, that is 103 units. 103 units. That means now you see 103 units means what? It is lying in this, na? 103 units is lying in this portion. Now, so by the algorithm, Q2 star is less than the prescribed range. That means it is not always. So you might see, na, that from this is a common phenomena. You might see that you should not always buy within certain range, na? That means some discounts are always available in the shops, na? Some big bazaars or metro bazaars or some this well-known well-known business models, na? They always give you some discounts. But does this discount should take you or not? Does this discount always gives you profit? It should not be, na? This is an example that we should not always we should not always take the discount to actually discount may eventually give you eventually give you loss only. Okay, sometimes, but sometimes it may be profitable for you, but sometimes it may be discount. It should not use. Okay, so you see that Q1 star is 100 unit. Q2 star is less than prescribed range, that is 200. So therefore we have to calculate the Q1 star. So Q1 star you get 100 unit. Now for this Q1 star equal to 100, we are calculating this total cost, and this upper limit is 200, na, where this price breaks. So you see that for both of them, which one is less? Which one is less? Obviously, total cost Q1 star is less than total cost B. So your optimal order quantity is 100 units. You should always buy 100 units to get the minimum total cost, and profit will be maximum. So up to this are the some basic deterministic inventory models. There are so many probabilistic inventory models are also there. Since you all are not familiar with this inventory modeling, so I have not discussed probabilistic inventory model. So if there is any subsequent time I may get, then I will always also discuss. Okay. So at this point, I will ask you if you have any question or not. Please ask. So how to stop this presentation? Stop share.
Yes, sir.
So thank you, Dr. Debnath, for your extremely beautiful presentation on a topic of recent interest, that is inventory modeling. Now I request the participants to unmute their videos or on their videos so that a group photo can be taken. Then a formal vote of thanks by Dr. Kumar Sahu, young faculty member of the department. Please unmute your videos so that a group photo can be taken. Dear participants, please unmute your videos. So that a group photo can be taken.
How are you, sir?
Yes, I am good.
Please wait, sir.
Now it is over to Dr. Nirmal Kumar Sahu for vote of thanks. Dr. Sahu.
So thank you all for giving me the chance to deliver a talk with your esteemed distinguished faculties and research students. I can see Dr. Jadhav also there. So yeah, thank you all.
Thank
for
you,
your
sir.
kind session.
Thank you, Sunil sir. Good afternoon to all. Now my duty is to give the vote of thanks. It's the last part of the seminar. Esteemed Principal Prabhakar Raut sir, esteemed guest of honor Dr. Prasanta Kumar Roy and Dr. Bijoy Krishna Debnath sir, esteemed IQAC coordinator Dr. Sunil Pradhan sir, respected head of the Department of Mathematics Aurobindo Pandav sir, and other academicians join in this webinar, and my dear student. First, I would like to thanks to our honorable principal sir for helping and encouraging us to organizing a national level webinar on balancing number and their related sequence, and overview a talk on seminar inventory model. I would like to express my deepest gratitude to our research person, Dr. Prasanta Kumar Roy, the professor in mathematics in Sambalpur University, for his delivering a beautiful lecture on balancing number and their related sequence for our students. I know his lecture will be very helpful to our students. Thank you, sir. May I like to express my deepest gratitude to our another research person, Dr. Bijoy Krishnan Debnath sir, Assistant Professor in Mathematics, Tezpur University, Assam, for delivering a very heart-touching lecture on the related to inventory model. Now it is very important for the engineering, mathematics, and business studies. Thank you, sir. And I would like to thank to our convener and head of the department, Aurobindo Pandav sir, for arranging the national webinar. I would like to thank the other faculty member of our college to attend the webinar. May I like to thank our student to listen the seminar from first to last. Last but not least, I would like to thank our technical support who directly or indirectly help us to make the event successful. Thank you all. Have a good day.
Thank you, Dr. Sahu. Now the webinar is over. Have a best day. Thank you.
Thank you all.
In this webinar, our alumni are there, Rekha Lal is there, and Swagatika Marana is there, and they are the department alumni. Thank you all.